Welcome to this explainer. China just made history. They actually became the very first country in the world to approve the commercial use of an invasive brain-computer interface. It's called NEO, and it's specifically designed to help people with paralysis regain movement in their hands. For decades, the idea of literally controlling a machine with nothing but your thoughts, that was strictly science fiction, but we have officially crossed that threshold. Today, we're going to unpack this historic 2026 milestone. We'll look at exactly how the tech works, how it stacks up against other systems, and most importantly, what it actually means for patients.
Okay, let's look at our roadmap for today. We'll be covering 1. Sci-fi becomes medical reality. 2. The broken cable solution. 3. Neo versus Neuralink. 4. The AI translation magic. And finally, 5. Small movements, massive impact. Let's dive right in.
Section 1. Sci-fi becomes medical reality, the 2026 milestone.
So there's a massive jump from having a research prototype that just shows some potential in a lab to an actual prescribed treatment you can get in a hospital. Researchers have been testing these neural interfaces for years, right? But always in highly controlled environments. What makes 2026 so incredibly different is that this technology finally got the green light for commercial medical use, completely outside of clinical trials. This is literally the first time an invasive brain-computer interface has reached this stage anywhere in the world. Think about it like the difference between seeing a really cool concept electric car at an auto show versus a car you can actually buy and drive to the grocery store. One shows what's theoretically possible, the other is a real, tangible part of daily life and mainstream medicine.
Just as a quick refresher, a brain-computer interface, or BCI, is essentially a system that creates a direct communication pathway between your brain and an external device. Normally, when you want to move your hand, your brain sends electrical signals down through your spinal cord and your nerves, right down to the muscles to give the command. A BCI acts like a super sophisticated technological bridge that completely bypasses those traditional biological routes. It captures the raw data of your intention right at the source and routes it straight to a machine.
Moving on to Section 2. The broken cable solution, how NEO works.
Like we just talked about, your brain normally sends signals through your nerves to create movement. But I want you to imagine what happens when someone suffers a severe spinal cord injury. That physical connection gets completely blocked. The crazy thing is the intention to move is still perfectly intact inside the brain. The person is actively thinking, move my hand, but because that biological pathway is broken, the message just never reaches the muscles. The signal is effectively trapped inside the skull, just firing endlessly into a void.
So the absolutely crucial formula here is this: brain to computer to movement. Think of the human nervous system kind of like a complex telephone network. The brain is still eagerly trying to send messages, but the main cable is cut. Instead of trying to medically repair that biological cable, which, let's be honest, is incredibly difficult and often impossible right now, the BCI creates a brilliant digital detour around the damage. It captures the neural activity at the source, figures out the exact intent, and sends it directly to a mechanical output.
The NEO system, which was developed by Neurological Medical Technology, executes this digital detour in 4 really seamless steps. Step 1, the patient simply imagines moving their hand. Step 2, the coin-sized NEO implant, which has 8 electrodes sitting right over the brain's motor cortex, detects those microscopic electrical signals from the neurons. Step 3, artificial intelligence instantly decodes those firing patterns. And Step 4, it translates those signals into direct commands that actually operate a robotic glove worn by the patient. The glove then physically assists the hand in doing the grasping movement. It's a completely astonishing, closed-loop system where invisible thought is instantly turned into a tangible physical action. It's just wild.
All right, Section 3, NEO versus Neuralink, a matter of resolution. Naturally, whenever we talk about brain chips, we have to talk about Neuralink, right? And there's a distinct difference in philosophy here. NEO uses electrodes that are positioned on the dura mater. That's the thick, protective membrane that surrounds your brain. It deliberately avoids penetrating deep into the brain tissue itself. From a biological standpoint, this makes the surgery way less invasive and drastically reduces the risk of deep tissue scarring, which is a huge hurdle for implants that need to stay in for a long time. Neuralink's N1 device, on the other hand, uses extremely thin threads that go directly into the cerebral cortex to get highly detailed neural data. Think of it like photography. Neuralink goes deep for a high-resolution, pixel-perfect image of the brain's activity. NEO, meanwhile, opts for a surface-level approach. It sacrifices a little bit of that resolution for a much less invasive profile that might just be easier and safer to roll out widely. Both are incredible feats of engineering for sure, but they're tackling the same monumental challenge using very different physical methods. Let's look at Section 4, the AI translation magic, decoding intention. We really need to understand that the hardware alone isn't going to fix anything. Machine learning is the absolute unsung hero here. Every human brain constantly generates an enormous amount of electrical activity. It's basically a loud, chaotic storm of signals up there. So the true engineering challenge isn't just listening to that storm, it's picking out the specific electrical whispers that actually mean the patient wants to move their hand. Machine learning algorithms analyze these complex, noisy patterns and slowly map out how each individual patient's brain uniquely communicates. It's exactly like teaching a translator to understand a completely new language. The more examples the AI gets from the patient trying to move, the smarter it gets. Over time, it gets flawlessly efficient at isolating the actual intent from all the background noise, translating it into a smooth robotic movement.
Finally, Section 5, small movements, massive impact, the human element.
Holding a cup, picking up a ball, grasping a spoon, using basic household objects. Honestly, to most of us, these actions sound so incredibly simple. We do them automatically, without even a second thought. But for someone living with severe paralysis, restoring just one of these seemingly basic daily activities is a monumental, life-changing milestone. In rehabilitation medicine, getting back the physical ability to just feed yourself or independently hold a glass of water means a massive return of personal autonomy. It severely cuts down on the need for round-the-clock caregivers, and it gives patients back a real sense of agency. The positive impact this has on a patient's psychological well-being, their dignity, and just their overall quality of life, it's simply immeasurable. The technology making this happen is wildly complex, but the ultimate goal is beautifully, profoundly human.
And this new medical frontier is expanding at lightning speed. We literally went from decades of science fiction to the 2026 commercial approval of Neo. But this approval is definitely not the end of the story. It's the starting line. Researchers all over the globe are already taking this exact foundational technology and exploring how it can help patients affected by severe strokes, ALS, and traumatic brain injuries. As the AI gets smarter and the hardware gets even smaller, future generations of these interfaces might allow patients to control complex prosthetic limbs with pinpoint precision, or even communicate fluently through text-to-speech when their vocal cords no longer work.
So I'm going to leave you with this final thought to ponder. Just look at how far we've come to reach this specific milestone. The era of recovering lost movement has officially begun. The question is no longer whether we can bypass the broken cables in our bodies, but rather how fast is this technology going to evolve to restore true independence to millions of people. Thank you so much for joining me to explore this incredible leap forward. Keep wondering, keep learning, and I'll see you in the next explainer.